chosen the image of the Gateway Arch in St. Louis to represent our exponential and logarithmic function section because earlier when we were learning about quadratic equations of parabolas, we pointed out that despite the fact that the Gateway Arch looks like a parabola, it is not a parabola because the points on the center curve do not satisfy the criteria that every point is the same distance from a fixed point called the focus and a fixed line called the directrix. Instead, the Gateway Arch in St. Louis is a type of curve called a hyperbolic cosine, and a hyperbolic cosine involves exponential functions. An exponential function is one in which the variable is any exponent. And exponential functions model a lot of important things, including the Gateway Arch. The inverses of exponential functions have been given the name logarithmic functions. So in this section, we will be studying exponential functions and their inverses, logarithmic functions. Basic exponential functions are of the form a times base b to the kx. A is the leading coefficient of the function, b is the base, and k times x is serving as the exponent. K is the coefficient of the variable. Here we have an example with leading coefficient 5, base of 2, k of 1.2, which is the coefficient of x, and 1.2x is serving as the exponent on the base of 2. This is an increasing function that increases fairly rapidly, although notice when x is negative, the graph rapidly levels out near 0. It will never actually equal 0 because it is not possible to find any value of x that will make the value of this function 0. So we say that the x-axis is a horizontal asymptote for this function. Also notice the y-intercept. We're crossing the y-axis at y equals 5, and that is the leading coefficient. We're going to pretty much stick to this basic form in our section, although after we cover the next section, we will point out some graph transformations. There are good reasons why we've denoted that we're not going to let a equal 0. We're going to make sure that our base is positive, and we're not going to let k equal 0. Here we have k equal to 0, and note my function is just a horizontal line, y equals a. In this case, it was y equals 5, because the leading coefficient was 5. So when we multiply 5 by any base to the 0 power, any value to the 0 power is 1, and so 5 times 1 is 5. So if k is 0, then our function just collapses to a horizontal line. And we've already covered horizontal lines. So we're going to denote that we're not going to allow k to be 0 for our basic exponential form. There is also a good reason for a not to be 0. If a was 0, then the function would be the horizontal line y equals 0. And we've already covered horizontal lines. So again, it doesn't really make sense for a to be 0 because the function just collapses to a linear function. It also really doesn't make sense for the base to be 0 because once again the function would collapse to the horizontal line y equals 0. And it would be undefined for negative values of x, since a negative exponent means the reciprocal, and we would be trying to take the reciprocal of 0, which is certainly undefined. Now if the base were negative, it creates an interesting situation in which the function would be defined for some values of x and not for other values of x. Remember, in the set of real numbers, negative values cannot be used as an input to an even root. So any value of x that would make that equivalent to an even root, like a 1/2 power or a 1/4 power or a 5/2 power or a 7/4 power, the function's going to be not defined in the set of real numbers. So notice here our graph consists of some dots because you can define that expression for some values of x, but not others. And there's constantly going to be gaps, and we would be hopscotching from values of x where the function is defined to values of x where the function is not defined. Hence, let's just not make the base negative. The bigger your base, the steeper the exponential function. Here we have exponential functions with base 2, base 4, and base 10. Notice the base 2 function is the least steep of the three. The base 4 function is somewhere in the middle, and the base 10 was rising pretty rapidly before it got cut off of the page. Now, the leading coefficient and the coefficient of x, k, those can also affect how steep the graph is, but in general, you should have an understanding that the larger the value of your base, the steeper the exponential function becomes. Increasing exponential functions can be written with bases that are less than 1. If they are, then the exponents have a negative coefficient. That's due to the idea of what a negative exponent is defined to be. For example, 5 times 10 to the 1.2x is the same function as 5 times 1/10 to the negative 1.2x, because 1/10 to the negative 1 power is the same as 10, as well as 5 times 4 to the 1.2x would be equivalent to 5 times 1/4 to the negative 1.2x, and 5 times 2 to the 1.2x would be equivalent to 5 times 1/2 to the negative 1.2x. Notice my bases are in parentheses. Only the base is being raised to those powers. The 5 is not being raised to the power. So make sure that when you are typing things in a calculator or in Excel, you are interpreting the base correctly and leaving the leading coefficient out, because it should not be raised to the exponent. Remember from rules of exponents that a negative exponent means the reciprocal. So 5 times 4 to the negative 1.2x is equivalent to 5 times 1/4 to the positive 1.2x. And same goes for 2 to a negative exponent being equivalent to 1/2 to a positive exponent, 10 to a negative exponent being equivalent to 1/10 to the same exponent but now positive. Notice that the larger the denominator, the steeper the graph, but because the graph is now a reflection about the x-axis, the steepness is on the negative side of the x-axis. So if you change an exponent to negative, or you take the reciprocal of the base, you're going to get a reflection about the y-axis. Logarithmic functions is the name given to the inverses of exponential functions. Here we have the exponential function, leading coefficient 5, multiplying a base of 2 raised to the exponent of 1.2x. The base of that exponential function is 2. Its inverse function will be expressed as log base 2. For this particular exponential function, its entire inverse function is 5/6 times log base 2 of x divided by 5. Note that the exponential function has a y-intercept of 0, 5, and the log function has an x-intercept of 5, 0. Remember, with inverse functions, you reverse inputs and outputs. So what was an x will be the y on the inverse function, and vice versa. So we have a couple of other points that we see are reversed. On the exponential function, when x was 1.5, y was approximately 17.411. On its inverse function, the log base 2 function, when x is 17.411, the output, or y, is 1.5. On the exponential function, if a negative 2 is put in for the input of x, the y is approximately 0.947, but on the inverse log function, when x is approximately 0.947, the output, or y, is negative 2. Remember, all inverse functions are reflections of each other about the diagonal line y equals x. We pointed out earlier that unless the leading coefficient was negative, exponential functions will never equal 0 and never have negative outputs. So our function here, which has a positive leading coefficient of 5 and base 2 raised to the 1.2x, has no values of x that we could find and plug in that would make the function equal to 0 or to a negative value. Now we could plug in values that have large magnitude that are negative, so like for example negative 10 or negative 20. The more negative the x value, the smaller and smaller the value of the exponential function would be. And so the exponential function, as x becomes a more and more negative number, levels off near 0. So it skims along the x-axis. So it almost gets equal to 0, but not quite. So the x-axis is a horizontal asymptote for the exponential function. Now its inverse function is not going to have any inputs that are negative or 0. So the domain for log functions are x greater than 0. It's undefined to plug in 0 or negative values into a basic log function. And the log function, instead of having a horizontal asymptote, has the reflection of that horizontal asymptote or a vertical asymptote. So the y-axis serves as a vertical asymptote for the inverse log function. Continuing to point out the inverse aspects of the logarithmic functions. For exponential functions, the higher the base, the steeper the graph of the exponential function. So for log functions, the higher the base, the flatter the log function. As x gets greater, the slope gets less and less. The slope starts to flatten out. But notice log base 10 is a much flatter, lower sloped graph for larger values of x than the log base 4, and the log base 2, it has the steepest slope, although it's not very steep, but the slope of the log base 2 function as x becomes higher numbers is steeper than log base 4 or log base 10. So again, the larger the base for a log function, the more flat the curve as the x values get larger. And that's somewhat inverse of the exponential functions. For exponential functions, the higher the base, the steeper the graph. Let us focus here on a very simple exponential and log pair of functions. We have y equals 2 to the x as our exponential function, and its inverse function has notation log base 2 of x. They are inverse functions, so what is the input of one is the output of the other. So the exponent on an exponential function becomes the output for the log function. Remember that negative exponents are defined as the reciprocal. So when x is negative 4 for 2 to the x, you get 2 to the negative 4 power, which means 1 over 2 to the 4th, or 1/16. So when I plug negative 4 into the exponential function, I get an output of 1/16. If I plug in negative 3, it'll be the reciprocal of 8. So it'll be 1 over 8 or 1/8, etc. Now 0 as an exponent will always give you 1. So for a basic exponential function like this with a leading coefficient of just 1, when we plug 0 in for x, the y-intercept is the point 0, 1. And as x then gets larger, the value of the exponential function gets larger and becomes steeper and steeper. So 2 squared is 4, 2 cubed is 8, 2 to the 5th is 32. So you can see the graph is, kind of soaring off the graph paper. Now the log function, the inverse function, when you plug in 1/16 as the input to the log function, the output is the negative 4. So what was the exponent is now the output. When you plug in 1/8 to the log function, you get out negative 3. When you plug in 1/4, you get out -2. When I plug 1 into the log function, I get out 0. So 1 as an input will give me 0 as an output for all basic log functions, because any base raised to the 0 power equals 1. So the log is reversing that. Now an input of 1 is going to always give us 0 as an output. And then as x gets larger, the value of log gets larger, but it's reporting back what the exponent would have been on the exponential function. So when I plug 32 into log base 2, I get out 5. Spend a little bit of time getting used to seeing this new notation. Think of log base 2 as a vocabulary word that means the inverse or reverse of the exponential function with base 2. So again, if 32 equals 2 to the x, log base 2 of 32 is going to tell me what that exponent is. It's the reverse operation. If you want, you could also get used to kind of canceling out the log base 2 with the exponential base 2, because inverse functions cancel each other out. That's their jobs. So you may want to develop that little habit of kind of crossing through the log and the base of the exponential function to illustrate to yourself they cancel each other out and give you what the input was. So in this case, if 32 equals 2 to the x, the exponent had to be 5, therefore log base 2 of 32 equals 5. Again, the log notation is just the made-up vocabulary that means the inverse or reverse of an exponential function. Here's a little more practice with this new vocabulary. If 100,000 equals 10 to the x, there's some power that I could raise 10 to equal 100,000. Log base 10 of 100,000 tells me what that power is. 100,000 is 10 to the 5th, so log base 10 of 10 to the 5th. Notice I can use that little trick of canceling the inverse functions. Log base 10 cancels out exponential base 10, leaving me with 5, which was the input of the exponential function. So log base 10 of 10 to the 5th is 5. If 625 equals 5 to the x, then log base 5 of 625 is going to equal 4, because 5 to the 4th power is 625. So notice again, if you write 625 as a power of 5, then you can kind of see how log base 5 and exponential base 5 cancel each other out, giving you 4. So log base 5 of 625 is log base 5 of 5 to the 4th is 4. 16 to the 1/2 is equal to 4. So log 16 of 4 is 1/2, because 16 to the 1/2 power equals 4. So again, if you rewrote 4 as 16 to the 1/2, you could see how log base 16 would cancel the exponential base 16, giving you the 1/2. How about 3 to the -2? Remember, a negative exponent means a reciprocal, so 3 to the -2 is equivalent to 1 over 3 squared, or 1/9. So log base 3 of 1/9 is -2. Because if I rewrite the 1/9 as 3 to the -2, I could see how the log base 3 and the exponential base 3 cancel each other out, giving me the input of -2, which is now my output. It was -2 as an input for the exponential function. It's now -2 as the output for the log function. Earlier, we were referencing the exponential function y equals leading coefficient of 5 times base 2 of 1.2x, and we mentioned that its log function was y equals 5/6 times log base 2 of x over 5. Well, where did all of that come from? Well, in our earlier unit about inverse functions, we learned that to find an inverse function, you solve for x, and then you can swap the letters back as we're used to having x be input and y be output. So if we did that here, notice first of all that 1.2 is the same as 6/5. So 6 divided by 5 is 1.2. So I'm going to rewrite the 1.2 as 6/5. So my exponential function is 5 times base of 2 raised to the 6/5 times x. I am trying to solve for x. So first, work from the outsides. The most outside thing is that multiplication by 5. So divide both sides by 5, and you get y over 5 equals 2 to our 6/5 x. Now, where is the x? It is in the exponent. I need to undo an exponential function. That's the job of the log notation. Whatever I do to one side, I have to do the same thing to the other side. So I'm going to plug both sides of the equation into log base 2 because I'm trying to cancel exponential base 2. So y over 5 gets plugged into log base 2. On the right side, when I plug 2 to the 6/5 x into log base 2, remember the whole job of the log base 2 notation is to point out that you're canceling out the exponential function. So log base 2 cancels exponential base 2, and I then have on the left side log base 2 of y over 5 equals 6/5 x, which was my exponent. I still haven't solved for x. I need to get x by itself, and so x is being multiplied by 6/5. To cancel out multiplication by 6/5, I need to multiply both sides by 5/6, the reciprocal. So 5/6 times log base 2 of y over 5 will then finally equal x. And now I'll swap the letters because we're used to x being the input and y being the output, and there is where that inverse function came from. The inverse function of 5 times 2 to the 1.2x is then 5/6 as a leading coefficient times log base 2 of x over 5. A special irrational number that works very nicely with exponential and logarithmic functions, and it has been given the name e. And it is approximately 2.7182818, but just like the other, another famous irrational number pi, its decimal expansion truly never ends and it doesn't really repeat. So it's kind of best to just write it in its symbolic form of e. It has the definition that it is the limit of the function 1 plus 1 over x raised to the x, and as x gets larger and larger and larger, the value of that function approximates this value, which is kind of close to 2.718. But you'll never truly reach infinity, and so you're never going to truly finish reaching the final limit of that value. So we express it as this irrational number e. Again, it's approximately 2.718. It gets used in a lot of exponential functions because of that definition. For example, if you take the compound interest formula, 1 plus rate divided by number of compoundings raised to the n times t, and you do a little bit of algebra, because of the definition of e, as the number of compoundings gets higher and higher and higher, so if you compounded your interest every millisecond, that limits to the principal times e to the r times t, where r is the interest rate and t is time in years. So that's one famous use of this special value e. We can see our gathering a turtle seems to be growing exponentially on that log. If you have the exponential function with e as the base, so y equals e to the x is basic exponential function with e as the base, it has an inverse function just like all exponential functions. It is log base e, just like all the other exponential function inverse functions. But because E gets used so often in formulas in science and finance, it gets special log notation. So again, it's just notation made up to mean its inverse function. Its notation is ln. So ln of x means the log base E function. It is called the natural log. So the ln is L for log and N for natural. In Romance languages like French, for example, the nouns often come before the adjectives, so that's kind of where that comes from. So again, it's log, natural log, logarithmic, natural. ln is the notation for the inverse function of e to the x. We'll spend more time on solving exponential and log equations in another unit, but let's do a fairly simple example on a concept called doubling time. Suppose we have 3,500 turtles in this ecosystem, and we are interested in how long it would take for the population to double to 7,000 if they are currently growing at a continuous rate of 6.93%. So we're assuming continuous growth, and our initial value is 3,500 turtles. So my leading coefficient is 3,500. I'm assuming continuous growth, so we're going to use E as our base of our exponential function, and the rate is the coefficient of the variable t. So 0.0693 is our 6.93% written in decimal form. We want to set that equal to double the initial amount. 7,000 is double 3,500. So the very first step, work from the outside in, is to divide by 3,500 to cancel out the multiplying by 3,500, and we then get the simple exponential equation e to the 0.0693 times t equals 2, because 7,000 divided by 3,500 is 2. And by the way, any doubling problem that you're going to do, you can just automatically skip to that step, because you know that the amount you're trying to reach is double the initial amount. Our variable is in the exponent, and so we are trying to cancel the exponential function. So plug the exponential function into its inverse function. Remember, ln is the notation to represent the inverse function of exponential base e. And whatever I do to one side, I have to do the same thing to the other side. So 2 also gets plugged into the natural log function. So the natural log cancels out the exponential function, giving us the variable component. 0.0693t is then equal to natural log of 2. To solve for t, divide by the 0.0693, and we see that it will take approximately 10 years for the population of turtles in this ecosystem to double. So again, that's an example of what is called a doubling time problem. You're looking to see how long it will take for a population to double. For both exponential functions and logarithmic functions, you can rewrite any base as any other base. Again, with the exponential and log functions, remember, you don't want the base to be negative, and you don't want the base to be 1, and you don't want the base to be 0. So still following all of those principles, any base can be rewritten as any other base. And we have the basic formulas on how you rewrite exponential bases and how you rewrite log bases. So if I have base b raised to the x, I could write it as some other base a, and what changes is the exponent. There's now a coefficient in the exponent, and that coefficient is log base a of b. And again, you can use that formula with any bases that you're trying to change. Now for logs, if I have log base b, you can rewrite log base b as some other base c, and the formula that you follow is log base c of x, the input, divided by log base c of b, the previous base. And again, that formula can be used to change any base into any other base. Looking at a few examples of changing bases, if I have base 2 as an exponential function, so 2 to the x, and I wanted to change it to base 5 for some reason, following my formula, I can just rewrite it as base 5, but the exponent will now be x times log base 5 of 2. And if I plug the same number in for x on the left-hand side, 2 to the x, as I do on the right-hand side, 5 to the x times log base 5 of 2, I will get the same value. They are equivalent functions. How about 1.08 to the x? If I wanted to rewrite it with base 2, it would be 2 is now the base, and the exponent is now x with a coefficient of log base 2 of 1.08. Log base 2 of 1.08 is a number. It is some number multiplying the x and the exponent. Often you're actually wanting to rewrite bases as base e or base 10 because base e and base 10 are commonly used, probably e even more than 10. So if I rewrote 1.08 to the x as base e, then e now becomes the base, and then I have my variable x. It's being multiplied now by a coefficient natural log of 1.08. So again, natural log of 1.08 is some number. You could hit the ln button on your calculator and type in 1.08 and it'll give you the value. And so 1.08 to the x is equivalent to the function with e as the base, but the exponent now has a coefficient of natural log of 1.08. And plain old 2 to the x would be equivalent to e to the x times natural log of 2. Again, you often see bases being turned into base e because calculators and Excel and programs, have base e programmed into them and have buttons and functions that are specifically assigned. How about changing some log bases? So log base 2 of x. If I wanted to change it to base 10, because my calculator also has a base 10 button on it, then log base 2 of x would be equivalent to log base 10 of x being divided by log base 10 of 2. So notice the input of the function is the input of the log base 10 in the numerator, and the base 2 in the log is now the input of the log base 10 in the denominator. How about log of base 1.08 with x plugged in, changing it to natural log? In the numerator should be natural log of x, the input. In the denominator should be natural log of 1.08, the old base. Log base 5, turning it into log base 10. In the numerator should be log base 10 of x, and the denominator should be log base 10 of the old base of 5. All of the important aspects of exponential and log functions and notation have been covered. Now we just need to practice.